Yeah. So welcome to my presentation workshop. So this is a design pattern for Faust DSP with a web-based graph editor. I would like to show you a tool that I made recently, which can be used for to design Faust DSPs in maybe a more straightforward way, just in a web browser. So first of all, I want to talk about why I chose Faust as the language to use in our DSP design workflow. One reason is that if your DSP is already written in Faust, it actually means that the DSP can be quickly exported with Faust IDE or some online service or with your Faust compiler to a large variety of platforms. And the other reason is that, which is also a most important one, that everything in Faust can be considered as an audio stream. You know, the Faust, the name is combined from functional audio stream. So everything is audio stream and everything is functional. So the way we design Faust DSP is just like connecting audio cables between different inputs and outputs from analog audio devices. So this reason actually brings us to the main purpose of this language. In fact, Faust language is designed to be an interpreter to calculate from an audio graph to some machine-readable codes, low-level codes. So it provides a very efficient solution to let us be able to describe some complex audio graphs into plain text. Then it's up to the compiler to make these texts understandable by machines. This process is called block diagram algebra. So this block diagram algebra is the powerful side of this language that takes care of both human users and machines. Its text-based form might be a sweet point, but it is still not easy to learn. Maybe Jan, you'll not agree with that, but from my experience, it's not so easy because to write in Faust, you need to learn how to manually translate a graph into the code. It means to flatten these cables and connections into plain text. And this needs sometimes hard work, especially for beginners, for sound engineer, sound designer, or artists. So, for example, without compilation, there's also some difficulty that we don't always know how much inputs and outputs these modules actually have if you are importing these functions from the library. So fortunately, a bunch of tools are provided to make the coding experience much better. That is why I wrote last year with Graham's colleagues to the new Faust IDE, in which users can watch your block diagram of the code written in real time, and you can test it with multiple visualizations. You can debug it very quickly, and just in the browser. So this is a big step, or even like a game changer for us to make the language more accessible and user-friendly to Faust developers. So after having this Faust IDE, I'm thinking about if we can go deeper or go further to this user-friendliest way. So I can share this. Maybe later. I will post it in the chat. This slide. So here's as Faust code is already a representation of an audio graph. Why not just generate it from a graph automatically? And that's so that we can design a Faust DSP without any coding. Here's what I imagine. We can, from left to right, we can start from a graph in the browser. We can do some patcher, and it generates automatically the corresponding code for you. And then you can test it or having this block diagram to recheck if it corresponded to your graph, and just in time and just in the browser. So this approach is also used by Jen. If you're familiar with Max, you might know that Jen is also a graph-to-code generator. There's a language called Jen Expert, which is also an intermediate step between. Yeah, maybe. It's the code is intermediate step between the graph and the DSP code. So you can also export this code into C++ code after you're having this graph or this Jen Expert code. So actually, I used Jen when I was making project in Max. So I think it would be nice if our Faust graph-to-code generator can handle shares the same behavior as Jen to facilitate Jen users or Max users to switch to Faust and export maybe to more destinations or platforms. Here are 4 behaviors in Jen that I implemented in the Faust graph-to-code generator. First is these boxes that represent a function that takes some arguments or inlets. Note that if you predefine one of the arguments, it will actually replace one of these inlets and replace them into a constant value. Then graph connected with these boxes is called a patcher. Secondly, when Jen analyzes this graph, it will iterate all the outputs and search the connections above. So without any connection, its inlets will be the default value, so 0. Then multiple connections into the same inlet will automatically be merged and added together. So this is the second image shows, and beside its code. So the out3 is without any connections from its inlet, so it will be 0. And out1 is the merge of in1 and in2. And if you need to introduce a loop into the graph, it should be delayed by at least 1 sample by the history operator. So this is similar to Jen's tilde, which is recursive composition operator. And Jen also supports 2 types of subprocess. You can use a code box to write Jen's code, or put a subpatcher. These subprocesses are especially useful when you want to reuse it in different situations. And then with these basics, how do we generate the Faust code from a graph? Let's take a look to some examples from these functions. We know that all of them can be formed as one identifier as a result equals the function's name with parentheses and arguments separated by commas. So here, from right, we have ma.sr, which is the sample rate. It has no input, so no arguments. Then the sign has 1 input and 1 output. So here it's sign 0 because it doesn't have any cables connections. For plus, it has 2 inputs and 1 output, and the os.oscrq which is oscillator based on 2D vector rotation, is special because it has one input and two outputs. So we need to give an identifier for each of these outputs. So the code is a little bit longer. Here are some more examples to show how arguments and connections affects the code. With the graphs inputs, they have their index and identifier and can be composed easily as a function argument. In addition to Jan's argument usage, you can use an underscore as a placeholder that allows you to omit an argument declaration and leave it as an input. For example, here we have from the right bottom, you have the en.ar, which is attack release envelope. It needs three inputs: the attack time, the release time, and the trigger signal. Here we fixed the release time, which is the second input, to 0.1, and the first input goes to attack time because we put an underscore at first position, and the second input goes to the trigger signal. You can also put a function name instead of the underscore or numbers to use it as an argument. Also, we know that for some pattern matching related Faust functions, the number of I/O is variable. It's more like the compiler doesn't know by default how much input and output these functions have if you don't put arguments before. So like here, you have si.bus 5, sorry. It should have 6 input and 5 outputs. So where the number 5 already occupied the first input, so it leaves 5 available inputs and outputs. You can declare by @in6 and @aus5, like in Max. You can have these properties to force these input and outputs. And generating a graph with a loop is one of the trickiest things in this system. We know that in Faust we need this recursive composition operator tilde should be used in a loop so that we can identify easily every loop in the graph. And this is actually Yann Oglaré's consideration, and he proposed to put all these loops outside the rest of graph, and then to facilitate the cable management. So in this case, we have the main graph has 2 inputs and 2 outputs, where one pair of them are used to build the loop. Yeah, you can see in this block diagram that the loop is outside the main graph. And here's an example of code block subprocess, where you can have some Faust DSP code as a subprocess. You can put directly the Faust code into this code editor, and you can. I use here the environment keyword you can see in the code to ensure that the subprocess is in a closure. Then just export the process function. And after each change of the code, I evaluate the code in this box to actually get information about the number of inputs and outputs, so that the outer graph can connect properly with it. And I also implemented the subpatcher that will be transformed into a width expression, in which you can use identifiers that are defined at the patcher at the parent level of the patcher. So here you can see in the doc represents the contain the inner side of the patcher object, and it's a max with 2 inputs and 1 output, and this can be reused multiple times if you want to duplicate it elsewhere. Yeah, and here's something that is quite special in Faust language, the iterators. More precisely, you have 4 iterators in Faust language, which is par, sec, sum, and prod. They accept actually a subprocess with a variable that changes for each iteration and starting from 0. So this means the box that represents the iterator should have corresponding number of outputs with an additional variable output that attached to the subprocess. So here we have a par3 means 3 parallel processes as the output. So we have first 3 outputs, and with an additional one at the right side, the 4th one that will attach to our subprocess. And in this outlet, the variable iterates starting from 0, and we are going to have oscillators with 3 different frequencies. And this results of the oscillator actually connects back to par3 object in order to close this subprocess, and then the par3 can know which subprocess to iterate. And in the code, you can see this subprocess is transformed to a lambda function. The last thing we need in this system is some UI components. Just as declarations in Faust, we can put some sliders, groups, knobs, and so on with its properties, the name, the main max, the default value, and the corresponding UI can also be generated in this web page. Okay, so yeah, maybe here we can start our workshop with some actual example of JSPatcher. Yeah, this environment is called JSPatcher, and I will post in the Google Meet this link so that everyone can try out. Yeah, and I propose you to open 2 tabs, one with this JSPatcher and another with Faust IDE, so that we can easily test our generated code. And yeah, you are invited using Chrome browser, because this web app is really optimized for Chrome. Safari will not work, and Firefox cannot do some copy-paste stuff of patchers. Yeah, and note that I just finished this version with a file manager this week, and yeah, I think there will still be some bugs not fixed yet. So you can ask me in the Google Meet chat if you're having problems or bugs. Normally, you just do Command S to save, or Control S in Windows system to save your patcher and refresh the web page, and everything can be working. Yeah, and another thing is that we have some limits about WebAssembly's memory. So maybe you also experience with Faust IDE is after too many times, if you compile these Faust DSPs, it will reach the limit of WebAssembly's memory. So when you identify that Faust doesn't compile in IDE or in JSPatcher, you just need to refresh the page. Okay. Yeah, I'm already sharing this environment into screen. So the first thing we're going to do is create from our file menu a new Faust patcher. So after doing this, you will have a tab called Untitled.DSPPad. DSPPad is the suffix of our Faust patcher. And if you press Command S, or you can do also save from file menu, you can save this patcher to the file system. We will call it 01 DSPPad. Yeah. But now you can see in your file manager panel, you have this this DSPPad already here, and this file manager will not disappear even if you refresh your web page or you restart your computer. It will always be there. It's just when you make some modifications of this patcher, it will display a yellow point to say that you are not saved yet this modification. So just press Command S or Control S in Windows to save it. Okay, so for the first object we'll create is a comment box that you can type actually things in it. This is a comment. You can press C on your keyboard, just like in Macs, or you can also press N to create a normal box, then type comment in it, and it will transform the box into a comment. And yeah, on the left panel, the first icon means you are writing the file manager, and you can also press the second one, which is a list of all the objects available in Faust patcher. So you can also type things in it and drag and drop the comments into the patcher. So that if it doesn't work, maybe it means your patcher is locked. So you can click on this lock to lock or unlock the patcher. So if it's locked, you cannot actually modify the patcher. For some cases, like the code, you can only edit the code when the patcher is locked. So yeah, you have two states of the patcher like in Macs. So we were creating our first patcher with some math operations. Yeah, let's just start from constant value. So if you press N and type C, you will have an object called constant or just C, followed by a number. We'll put 0.442 as an example. So in this, this box will actually output always the constant number 0.42. And we will create another object called out. Out1 means the first output. Just connect them together. And you can see in the code from the right side, you can press, click on this code button to show the actual code of your patcher, and you will see it already have the out1 equals constant, this constant box, which is 0.42. And actually this code changes when you have any connections changes in your patcher. So yeah, I will just put some comments here. Constant value. I do this. And if we are doing some math, maybe we will add some value onto it. just type n and plus space, then 0.42. And we'll create another output here, out2. Our output 2 is not connected, so it's 0. And when I connect it, it becomes the sum of these two values. You can also having plus objects without any arguments, just have two inputs, so that you can connect 0.42 onto it, and actually you will have the same result as out2. Yeah, then we will maybe do all the other operations, not plus, but minus. You can do Command D or Control D in Windows machine for duplicate these boxes. And double click the boxes to change the code in it. So this is the fourth output. This is the third, fifth, divide, multiply. Okay, now we are having all 5 outputs in this process. So let's just have it test in Faust IDE. So I'm going to switch to Faust tab here. And copy paste the code we are having, and we'll do an offline plot to just having these numbers on the screen. So put your plot mode to offline and plot first samples. Yeah, so now you're having strips with these values. I think they are correct. Okay. Yeah, I don't know if everyone got this result, but yeah, I think we will just continue. So this is our first patcher. Let's just save it, close it maybe, and create a second Faust patcher. So here we will do our classical example of the djembe example, when I think everyone, if you firstly you've opened the Faust IDE for the first time, you will see this example, and it actually outputs a physical model of a string that repeats and repeats. So we will just put the code here. You can have a code block with the code object like this, and I will post this code, this example code here. So you know these objects of coming from Faust standard library, and here in Faust Patcher you already have all of them. So if you see not seeing the objects.
Ren, we still see your Faust IDE.
Oh, sorry. I need to switch. Yeah.
Thank you.
Yeah, thank you for the reminder. Yeah, so here, well, I'll redo the process, don't worry. I will put code in object. I will put a comment here. This is code block, and I'm pasting our example code. So let's do this example with a patcher. So you know, everything in Faust standard library are also available in this patcher. So you can find all this ba.posen, which is the one post every 10,000 samples function. So let's just put da.posen and 10,000. It has one output and it will be connected to pm.gmb. With all these arguments separated by space, connected, and pm.revert demo. Revert. And this output of Jambe should be connected to all of these two inputs of the demo. And dispatcher will have two outputs. Connect them together. Now we open code and it will generate a code a little more complex from the original one, but basically it's the same. So we put this in Faust IDE and we are having a diagram. And yeah, and to switch tab, yeah, we are having this diagram and we can run the code and it's working. So yeah, we will be able to run this code also in this JS patcher environment, but let's just continue with some other patches and test them in JS patcher. So yeah, I will just save this patcher as the second one. And we can start from build a third one, another patcher. Yeah, so in this patcher, we will build a very simple algorithm or DSP, which is the mean value of one period of incoming samples. So we will build a subpatcher and test it with the main patcher. So we can put a subpatcher here. You can put P for short or patcher. Yeah, the same thing. And you can actually double click the patcher to show what's inside. And you can also do Control Enter to display the patcher at the red panel. You can also modify it here. So we'll do this like this. So what's the algorithm for that? Basically, you have an input calculate, and you have a second input, which will say how long this period is, how much samples you want to calculate for this main value. And the first thing we will do is delay our incoming signal for this period. We use this add to delay a false signal to some samples, and then you can minus the actual value from a sample that's is n samples ago, like this. And then we do an integration. Just add all these samples together between this period. So we need to add them together with a loop that feedback like this. And here we have the sum of n recent values. And the last thing is to divide it by the number of samples we measure. And output. You can see the algorithm here. And in order to test this, we may want a sample integrator with one value incremented each step by 1. So the same thing here. Plus, we can do copy paste actually. Okay. And we also need to decide the length of our measurement. So let's put 400. And out 1. Okay. So this should be, if it works as expected, after 400 values, you will have the sum, the mean value of the sum of the first 400 value. So let's put the code in Faust ID. I don't know if the add doesn't exist. Maybe you are not in a Faust patcher, you are in another patcher. So make sure you choose the Faust patcher in your file menu. Let's put here in Faust ID and plot offline. And you will see here the 400 value. You will have a result of like 200 or something. So it works. Okay. The next thing, if we already have the algorithm of this mean value, we can actually build an IMS measurement in our Faust patch. So let's just save this one. Oh, I think we should do it quickly. So maybe just copy paste this patcher here. So in order to do RMS, which is root mean square, in fact, you have 3 steps. The first step is do a square, each values. And you already have the main, these values. So we will put another 400 here.
Sorry, we are seeing again just the Faust.
Yeah, sorry. Sorry again.
Thank you very much.
Yeah. So I'll put some comment here. This is square. And you have the mean, and then the root. Root. Okay. And we will be able to display the value in bar graph in Faust's UI. So it is called IMS from 0 to 2. And you will need a attach for that you doesn't lose your signal and the signal doesn't be considered as 0 of 1. So this will show a root main square of the input value, and let's just test it in our patcher. So we just need to resave it 04. And let's create a JS patcher, which is a little bit different. It's not a Faust one, so it will not generate code, but it's a runtime for you to execute or compile the Faust code or compile this graph. So now you're having a new JS patcher in which you can put a Faust patcher inside using pfaust with a path. So the path is 04.bsp_path. Yes. And I don't know, maybe an oscillator. So this is a web audio oscillator, which is not coming from Faust, but we can build an oscillator from Faust later. We don't have much time today, but yeah. So to have this UI, you can simply type UI or Faust.ui because it's under Faust namespace. So if you type Faust.ui, you will have this empty box in which you need to connect from the last output of pfaust and connect it back to the first input. There are keyboard shortcuts go in and out. Yes, it's actually command click the space in the patcher. Yeah, so you will also need a bang. You just press B on your keyboard and you will have this button. You can lock the patcher to ban this Faust patcher in order to have this graph, this UI. And after connect this oscillator, make sure that you also click this. You have this little button. It's an audio switch. You need to enable it to have your audio. And I think it's not working. Let me see. So I don't know why it's not working. Maybe it's because Faust is not compiling. Okay, yeah, I don't know why you need to connect the output of Faust to some destination in order to get it to work. So here is an object.
Got optimized away, maybe.
Sorry?
Maybe the output just got optimized away. I mean,
Yeah,
Faust
yeah.
is highly optimizing.
Yeah, I think it's more web audio optimization. If it's not connected, it's not working anymore. So here it will work if you connect this live gain object to the output of this PFOS. You can listen to it if you put audio in. And yeah, this output. Yeah, it's not this output. Maybe it's this one. Okay, this output is not actually a signal to hear. So yeah, we'll have this RMS, and yeah, this to test it. Maybe we can just do it like this to actually change the volume, and it works. Yeah. And let me see what else can we do. Yeah, maybe to do it quickly, we can have some MIDI stuff. So I will not do step by step, but I will just copy paste a patcher into this environment. So let's make a new one. Yeah, Faust patcher. And here we can have an example like guitar UI MIDI maybe, and directly connect it to output. So by default, I think it will basically enable the MIDI function, and maybe you will need some effects, general effects, which is a reverb, for that all the voices have the same effects group. So to enable this effect, you need to do like iterators, just connect it from its output to its input. So it will just compile the effect for you. So now we have a MIDI ready patcher. We'll call it MIDI. Then to test it in JS patcher, I will just put some code directly here. It will ask me if I allow to use MIDI devices, and yes. So here we have a bang. We have an object called MIDI devices. We have menu, allows you to choose which MIDI devices you want to use. So here's my keyboard. Basically, it will display what I'm playing. And I will put my Faust patcher here. MIDI.pad. And so to enable the MIDI function, you need to specify the voices it will use. So here I will put 8. And audio out. There's a 2. And maybe some volume control before. Okay, I don't know why the cables are disappearing, but I think it works. And let's just connect with the merger to have two channels. Maybe move this one. Yeah, merger before and then again after. Oh, I should only have one output, so just duplicate them. Okay. Yeah, I think we don't have much time to do further. Yeah, it's just it. If you have any questions. Yeah.
Yeah. Super
I think
nice.
Albert have some
question.
Yes, Albert Gray from the University of Mainz. Well, awesome work. I'm really looking forward to trying this out in my courses. So I'd like to ask you, I was a bit late for the session, so maybe you said that at the beginning, but what is this written in? Is it just plain JavaScript, or do you need any other special tools?
Oh, yeah. So basically, we are only using JavaScript and Faust. It's just under, yeah. It's just my understand. Just I need to understand correctly how Faust works and how to form these expressions, and yeah, the rest is just combined from JavaScript. And yeah, this is an open source project, so you can have it on GitHub.
This runs under Chrome, so if you have Chrome running in any environment and have a JavaScript engine, you can make this work, right? Did I understand that correctly? So we could make it run directly in Pardata, for instance, because that has a built-in JavaScript engine. But for starters, if I want to install this on our own web server for the courses that I'm doing, can you quickly sketch out the steps that I'd have to do?
Oh yes. So basically, it doesn't have any server. It's just a web application that can be run standalone or just offline. If you fetch these codes from GitHub, you will just run it quickly. Yeah, just like that.
Okay, thank you. Very nice. Thank you very much.
Shihong, is it a progressive web app?
Yes,
okay.
You can actually install from Chrome. And I think from some Android mobile devices, you can also use it. I not tested, for instance, but yeah, I think it works.
Yeah, I know that the Faust IDE works on my phone, for example. But
yeah, it's
Michel?
just the creation of these boxes and the connections. I don't think it can be done easily with a mobile device.
Sure,
but,
sure.
Yeah.
Michel, yes. We can't hear you, Michel.
Can you hear me now?
Yes.
Yeah. Oh, not anymore. Yeah, maybe I can just
yes.
ask.
Can you hear me?
Yeah.
Yes.
Is it better?
Yeah. Yes.
Micro. Hello.
We can hear you. We can.
Oh. Hello. Can you hear me?
Yes.
Okay. So because I have my sound card plugged. Okay. Well, my question was, can it work? Does it work on Firefox? Because Yesterday, I talked a lot with Paul Adeno from Web Audio, and he was really fed up of application that requires Chrome for web MIDI. He said, well, in Ableton, if you don't have a MIDI device, you can do audio projects. So I wanted to be sure that it doesn't run only in Chrome.
Actually, it works on Firefox, but it's just one thing. It will not work is copy paste.
Okay.
So if you copy a part of patcher and paste elsewhere, you will have problems.
Okay, maybe you can exchange. Maybe you can exchange with Paul Adeno in order to make this work, because he's now spending some time helping people making Chrome-only application work also on Firefox. So.
Okay. Yeah. Yeah, I need to respond to this documentation question, because this is really experimental and pre-alpha, so I don't have any documentation written. And actually, I just fixed some bugs today. So yeah, just if you want to know more about it, just look at the code on GitHub. So yeah, maybe I can put the GitHub link here. Yeah. I will stop screen share.
Okay. Do we have any more questions for Shihong?
Just one remark, if I may. Could you upload the examples that you did today?
Oh, yeah, sure. I prepared that, but it's just I'm not showing you the examples. Yeah, I will also paste all these things on the chat.
I've got another question, maybe, Shihong. I know, because we're working together, that you will be able to import external graphs or external plugins into your patches. Can you say a little about this?
Yeah. So it's a little bit off topic, because it's not for Faust, it's for JavaScript. So yeah, actually in JS Patcher you can use eternal like npm packages, yeah, to do more things like graphical processing or yeah.
I wasn't talking about this. I mean, you will be able to load web audio modules also written in Faust, for example.
Oh yeah.
Or can you also import gen patches or?
Yeah, good question. For web audio modules, yes. I don't know if I made the last modifications of the API here, but generally, if you have already written web audio module, it can be used as a plugin here.
Web audio modules are web audio plugins that you can export from the Faust IDE that can include a graphic user interface, and that will run in WebAssembly. So you can add them directly in Shihong's tool. And about Gen?
Yeah, Gen it's a little bit complicated, because Gen can do other things like buffer operating, or Gen can also do video stuff. So actually, I already ported a part of Gen into Faust. So in this link, you will find some Gen examples. It's just a copy paste to this Faust patcher, and it will just run. But you also have something that is not just import them and it can be run like this. So yeah, it's not simple like that.